Hello and welcome to this video in which we will show how to do the analysis of a single replicate of a 2 to the 4th experimental design using Minitab. It turns out Minitab makes this almost ridiculously easy. Okay, so here we have the results of an experiment that we've designed. The idea is to determine what factors affect the production of computer code by programmers. Now, I have to say, in all honesty, I just made the data up, but I thought it was pretty funny. One factor is whether it's light or dark in their cubicle. A second factor is whether or not you give them lots of pizza. A third factor is whether or not they have a large or small cubicle. The fourth factor is whether or not you give them lots or little Mountain Dew. The response to each of the variable combinations is measured in PPUs or programmer productivity units. Let's now do the experimental analysis. To do this, I go to Statistics, DOE, Factorial, and Analyze Factorial Design. So it complains because I actually haven't designed the experiment yet. So it asks if I want to give it the information that it needs, and I say yes. And the factors are going to be in columns 1 through 4. They're two-level factors in the sense that they're either +1 or -1. So I can go to low-high, and it actually has figured out that my low values for each factor is -1, my high values are +1. So I can say OK. And now I want to tell it that the response is PPUs. And now I also want to tell it that I want to have only second-order terms. If you're doing an experiment that has a single replicate, it's helpful to be able to use higher-order terms to estimate noise values, in particular to estimate the standard error of the effects estimates. So in this case, I'm going to tell it to include terms up through order 2. I'm going to tell it that I want graphs. I want an effects plot, a normal probability plot of that, and we'll let that be enough. And so I can hit OK. So these are the results that it gives me. For each of the effects, it gives me an estimate of factor effects as well as interaction effects. So A, B, C, and D are factor effects, and it gives me those estimates. Then it also gives me the interaction effects for all of the two factors combinations. It also gives me coefficients, this column, and these coefficients are the linear regression coefficients for the model that I get. It provides a standard error estimate for these coefficients and gives me a t-statistic, which I can use to test for the significance of the coefficients and the p-value associated with the t-statistic. Small p-values represent significant coefficients. So a p-value of 0 here says that the constant term is significant. The term B, which is the pizza term, is significant. Term D, which is the Mountain Dew term, is significant. And the interaction term of B and D is significant. All the others are not significant. If I look at my probability plot of the effect estimates, I can also see that D, B, and the interaction term are significant in the sense that they fall significantly away from the straight line, which represents a normal distribution. Now I can go back to the Analyze Factorial Design, and I need to check this box to give me a normal probability plot of my residuals from the linear regression model. So I do that, and it gives me a plot of residuals from my regression model. And you can see that these residuals fall more or less on a straight line, which means that residuals are more or less normal, which means that my regression model fits the data reasonably well, and I don't need other coefficients to improve it. Finally, if I go to Design of Experiments, Factorial, and go to Factorial Plots, tell it I want an interaction plot, and tell it that I want the interaction plot to be between pizza and Mountain Dew, and then select PPUs as my response, I get the following interaction plot. Because these lines are not parallel, it means that the factors B, which is pizza, and D, which is Mountain Dew, interact with each other, which means that I can't optimize programmer productivity units by selecting values for B and D independently. I have to do them together. And you can see from this that giving a programmer just Mountain Dew, and this black line here corresponds to no pizza, gives them the highest productivity. Giving them Mountain Dew and pizza actually reduces their productivity a little bit. Giving them pizza and no Mountain Dew gives you a reasonable level of productivity, but it turns out the very best you can do is just give them Mountain Dew and no pizza. So there we have it. Hopefully you found this to be helpful. Thanks for watching.